Hi, welcome to another lecture on business mathematics. Today we are going to continue the lecture on exponential and logarithmic functions. This is going to be part 2, and we are going to talk about exponential equations. So last time we introduced you to b to the power of x and e to the power of x. B is some base. Famous bases are like 2 and 10. E, most famous base, is this peculiar number 2.71828. And in fact, the origin of this number is in business mathematics. It was introduced to calculate certain compound interest. So if you buy any kind of a substantial item that is going to come on an installment, to calculate your installment, these functions get to be used. Any kind of business transaction that happens over an extended period of time will rely on these functions. So we are going to go and look at the mathematical properties of these, and hopefully we can explain what the applications they have in business mathematics itself. So today we are going to talk about exponential equations. What does that mean? Let's start by some simple examples of exponential equations. So that is let's start with a very simple example. Suppose we want to solve the following equation. 2 to the power of x is equal to 8. What is x? Now remember, 2 to a whole power means you are multiplying 2 by itself several times. So if you start with 2, you multiply it by itself again. So by now I have 4, and by now I have 8. So x counts how many 2's we had here, and our solution here is x is equal to 3. So if you remember that 8 is 2 to the power of 3, we can write our equation like this. 2 to the power of x is equal to 2 to the power of 3. And one of the properties of the exponential function is that if you have same bases on two sides, then the exponents have to be equal to each other, and that is how we get 2x equal to 3. Now let's go practice some basic cases, and then you try to answer before I give the final solution. 2 to the power of x is equal to 16. What x do I need here? So of course I need one more x, and therefore x becomes equal to 4. So we are solving this by trial and error or by memory. From memory we can tell that 2 to the power of 4 is 16, and therefore x will be 16, and so on. So 2 to the power of x, say let's go to a larger number, 128. So what does it take? So far 2, 8, 16, 32, 64, and now 128. So now I have 7 of these things. So x is equal to 7. Of course, as our numbers become larger or strange, the practice is not going to be very efficient, but it's good to get started. Let's go to some other cases. Suppose I say 2 to the power of x is equal to 1 over 4. Well, 4, I remember that is 2 squared, and last time we learned that 1 over b to the power of n can be written as b to the power of minus n. So I can write this as 2 to the power of minus 2. And by the observations that we had over there, if your two exponential numbers have the same basis, then the exponents have to be the same. So here I get that x has to be minus 2. Similarly, 2 to the power of x being 1 over 8, we can tell that x has to be equal to minus 3, and so on. Okay, now let's go to some more advanced problems. Suppose I write 2 to the power of x is equal to 8 to the power of 2x plus 5. And the question is, what is x in this case? To solve this type of problems, we write both sides with the same base. So 2 can stay as it is. Instead of 8, I remember that 8 was 2 cubed. So in these problems, both sides have to be written to the same base. So I'll have 2 to the power of x is equal to 2 cubed, the whole thing to the power of 2x plus 5. You remember the rule of exponent we had last time, that if you here this one, this is what gets to be used often in this case. If you have an exponential number raised to a new exponent, then the two exponents multiply each other. That's what we explained last time, and now we are going to use that idea. So what I have here is I have to multiply these two exponents, 2 to the power of 2 to the power of 3 times 2x plus 5. So that is 2 to the power of 6x plus 15. Now, two exponential numbers with the same base. The important thing is that the bases have to be the same. Once they are the same, then we say the exponents have to be the same. So I take 6x to this side. So I subtract 6x from both sides. So this becomes minus 5x is equal to 15. Therefore, x has to be 15 over minus 5. And our answer is, this is minus 3. How do we check our answer to make sure we haven't made a mistake? Plug it back on both sides and see if it is actually true. So instead of x, I put minus 3 and I ask, would the two sides become the same? So I'm verifying to make sure I have not made a mistake in my calculations. So this is 2 to the power of minus 3, and we are asking a question, is it same as right hand side? 2 times minus 3 is minus 6, so this is minus 6, plus 5 becomes minus 1. Well, are they the same? 2 to the power of minus 3 is 1 over 2 cubed, and this is 1 over 8. Are they the same? Well, yes, because 2 to the power of 3 is same as 8. So this question mark checks we actually got the correct answer. Let's do another example of this type of questions. So suppose I have say 4 to the power of x squared, and on the other side I have 8 to the power of 2x. I'm going to solve this. You have to write both sides with the same base to be able to compare them. So instead of 4, I write 2 squared, now to the power of x squared. On the right hand side, I write 2 cubed to the power of 2x. Remember, all the new exponents have to multiply, so this becomes 2 to the power of 2x squared. On the right hand side, 3 times 2x is 6x. Now the bases are the same, and we say the equality can happen only if the exponents are the same. Now I have some equation by setting these two equal to each other. Whatever it is, we go back to the lessons we learned at the beginning of semester. It's a quadratic equation. You can solve it by factorization, by quadratic formula, or whatever you like. So in this case, I have 2x squared minus 6x equal to 0. Brought everything to one side. I factor a 2x, and then I have x minus 3 equal to 0. We set each factor is equal to 0, one of them has to apply, so either x is 0 or x is equal to 3, and these are our answers. You can verify by putting them back and simplify, and to see that they are actually the same kind of we have the same number on both sides. Okay, let's go ahead and do some practice on graphing. Suppose we want to graph y is equal to 5 halves to power of x. Well, we have done graphing in general. Remember, we so the idea of graphing is the same. The details of the function could be somewhat different, but we are going to do essentially the same every time. Make a table, make a set of points, and then just graph them. So here I have my x and y. We have to see what are the relevant pieces of the graph, important points, and try to capture them. Here everything happens around the center, so x, I choose it to be these type of numbers, -1, -2, -3, and then 1, 2, 3. And of course, if my patient allows, I have more of them. So when I put 0, anything to power of 0, you remember, anything to power of 0 is 1, except of course 0 itself, but any other number raised to the power of 0 is 1, so that is 1. At the 1, my exponent is 1, so I have just 5 halves. At 2, 5 halves squared. What is 5 halves squared? So that's 5 halves times 5 halves. 5 times 5 is 25. 2 times 2 is 4. So 25 over 5. You can divide this 6.25. Sorry. Or from beginning, you could have divided 5 by 2 and then square that. At the end, you get the same answer. So 6.25 or 25 over 4. Let's write the approximate value of these things, 6.25 to the power of 3. 5 half cubed is the same as 5 cubed over 2 cubed. So 125 over 8. What is that? So we use our calculator at some stage here and get 15.625. So that is 125/8, which is 15.625. You want to do some of the basic ones by hand, and as the problem gets complicated, then you want to use decimals. So for -1, I get 5 halves to power of -1. You remember, if a exponent is negative, same as the fraction with same exponent as positive. In particular, if I have a fraction raised to a negative exponent, a quick way to get to the answer is to take that fraction and flip it and raise to the positive exponent. So 5 half to power of -1 is same as 2/5 to power of 1, which is 2/5, but that is 0.4. Same way, 5 half to power of -2 is same as 2/5 to power of 2, and that's going to be 4/25, and that's going to be 0.16. Finally, 5 half to power of -3 is same as 2/5 to power of 3, and that's going to be 8/125. and that's going to be 0064, I believe. All right. Okay, once you have all these numbers, you can try to graph them. In the exponential functions, your numbers grow quickly, so you have to be careful about that when you are graphing. So suppose I take this thing to be 1. First point, let's maybe point them in red, is this point 1. At 1 we have 5 halves, which is 2.5. So 1, 2, 3, and 2.5 is going to be here. At 2, I'm going to be at 6. 1, 2, 3, 4, 5, 6, 7, 6.25. I'll be here. So this was 2.5. This is 6.25. At 3, I'm going to go way up. So this was 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'll be somewhere here. You see that it explodes. That's the property of exponential function. They go up quite rapidly, and that is something special about compounding. So when they say try not to have debt on a credit card, because it's the same way, it grows very quickly and gets out of hand. How about on the negative side? Let's say -1, -2, -3. At -1 we are at 0.4, so it's going to be low here. The next one is much lower, and the next one is barely perceptible above the x-axis. So this, on this side, you have a picture that looks like this. When you go up like this, this is referred to as exponential growth. Example of that is, of course, in compounding money. When you go in reverse direction, that's called exponential decay. And that is something that you see, for example, in the problems related to radioactive decay or absorption of light by glass and so on. They have this look to themselves. Sometimes you see it with a negative exponent. Let's do a simple example, 2 to the power of negative x. What does that look like? I'll be fast here. So you have x and y, so 0, 1, 2, 3, and -1, -2, -3. So at 0 we always have 1. Now we have 2 to the power of minus 1. Well, that is it, same as 2 power of 1, and that is 2. Same reasoning, this is 4, same reasoning, this is 8. This one is going to become 1/2, and 1/4, and 1/8. So when you graph this thing, so at the 0, we, as usual, we have 1. At the -1, we have 2. At -2, we have 4. At -3, we have 8. So 8, 4, 2, 1. As we march forward, every time we are being reduced by half, 1/2, 1/4, and 1, 2, 3. Finally, we have 1/8. If you connect these to each other, that's a graph of 2 to the power of -x. You see that we are going down. This is called exponential decay. Excuse me. Expo. And that happens in radioactive problems where a substance disintegrates to something else, and the amount that remains follows a pattern similar to this. Okay, so we learned how to handle exponential equations and some graphs with some variation on what happens at the base or at the exponent. Okay, for the next lecture, we are going to go ahead and concentrate on logarithm. Until then, good luck and God bless.